Right, so I'm just going to do I'm going to do a quick overview of sequences and series. So you had the packet last week that you read through. You did some problems with it. I'm just going to go over some of the main points from it, and do a few practice problems. So you have this as an extra resource as well. So sequences and series. The reason we're talking about it, it's kind of like a underlying thing of math. It's kind of going back to basics, looking at patterns and numbers. So we've done a lot of study this year over functions. And functions are cool, right? They have interesting properties. They help us do a lot of things. But a lot of times, functions don't always cut it. Sometimes we just have relations between things. Sometimes we just see patterns and numbers that aren't necessarily functions, but there's some interesting properties too. Sequences can end up becoming functions. We can talk about them as functions as well, but they don't necessarily have to be that. So this is kind of like just going back a layer on it, but not adding additional requirements. There are a few different types of sequences, and series are related to sequences. And really this year we're just kind of reminding you of it. You've done a little bit of this in the past. We're just kind of reminding you of a few things with it, doing a little bit more work with it, because next year you'll be doing a lot more work, especially with series. And if you go on to do some math in college, you'll do a lot of study of sequences and series, kind of, again, going back to the digging into maths, like deeper hidden layers that we don't usually talk about when we talk about functions. So we're just going to go over some main types of sequences. This is just a very select number of it, right? So when we're talking about sequences and we say like arithmetic and geometric sequences, because those are things you've heard before, those are not the only types of sequences that exist. There are a lot of sequences, any set of numbers. So let's define it, right? A sequence is just an ordered list of numbers. You can have finite sequences, so that's an ordered list of numbers that ends at some point. That's finite. That has an endpoint, has an end. Right, so this could be 1, 2, 3, 4. Right, I ended it there. It's a set of natural numbers. It's a sequence, but I'm stopping it at 4. An infinite sequence is still an ordered list of numbers, but this one doesn't have an end. It's infinite. That has no end. So this could be all the natural numbers, right? I could do 1, 2, 3, 4, 5, and go on and on and on. Never stop. Main differences on here. So this thing, you can pretty much categorize every sequence this way. Then there are a few special sequences we're looking at. And I only say special as in by giving it a special name. It doesn't have like a exalted place in math, I guess, but it's the one that we frequently talk about. So we have arithmetic sequences. The reason this is nice and we talk about it is like it's very similar to functions we look at. It's very much like a linear function. In fact, it works the same way. You can write it like a linear function. The only thing that stops it from being a line, the way we think about it, is a line is continuous. And this is going to be discrete because we're going to only list certain terms in it. We're not listing every single term, so you couldn't have a continuous line. But you could make a discrete function of this, put the dots down, and it'll look like a line. So an arithmetic sequence is something like 3, 5, 7, 9, 11. It's an ordered list of numbers that starts at some place and continues. It could go up, it could go down. But the main thing here is that it's changing by the same amount every time. We're adding 2 here, for example. In terms of lines, we would call this the slope of the line. In terms of sequences, we call this the common difference. When we're labeling things, the first term, so really all of these terms, we can label them with a variable for the sequence. Usually you'll see T used, meaning term, or A used. I usually use A. I don't really know where I got that from, but as far as I remember, I've always written this as A. But I've also seen T quite often. So I would call this A subscript 1, meaning the first term of the sequence A. Then 5 would be A subscript 2, 7 would be A sub 3, 9 would be a sub 4, 11 would be a sub 5. So you can count terms in the sequence. That's why it's ordered, because then I can ask you, what is the third term of the sequence? You know it's 7. It's definitely 7. It's not in a different order. So we can write an equation for it. This one's called we can write either an explicit formula for it or an implicit recursive formula. So the explicit formula looks like the line equation. It's like y equals mx plus b. So the way we're going to write this is we're going to say any term in the sequence. So I'm going to say a sequence term a sub n, meaning the nth term of the sequence, is going to be, well, when I do y equals mx plus b, I look at my y-intercept and I need the slope. So the y-intercept here would be a sub 0. It's what is the initial value when your x value, for example, is 0. So that would be, I'd have to go back a step, right, to positive 1. Now that's not part of the sequence, but it's just me figuring out the formula for this. So I can say this is 1 plus the slope 2 n, right? So then I can test it. When I plug in 1, I get 1 plus 2 times 1, I get 3. That's one way you can write this. You can also write this if you don't want to have to go backwards to a term that isn't in the sequence. We can start with 3, right, and say 2, but now I can't multiply it by n anymore because that will go too big. When I plug in 1, I'd get 5, but I need to get 3 again. So I can just adjust this to be n minus 1. Either way it works. In general, explicit formulas are going to be a sub n, which is, and then a 0 term plus the common difference times n, or a first term plus the common difference times n minus 1. The other type of formula you can write is a recursive formula. So this is something you might be more familiar with if you've been doing some of the computer science classes, you've been programming a little bit. It's what loops are based on. So we start off with talking about one term, and then we say how to get to the next term, and then we say how to get to the next term after that. So this is a very easy thing to write, but not as easy to calculate. When we do the recursive formula, I tell you what the first term is. So I'm going to tell you the first term is 3. And then to get to any subsequent term, so if you ever want to know what the nth term is, you go to the term before it, n minus 1, and add 2 to it. So now if I want to know what is a sub 2, well, I'd have to go to the previous term, which is 3, and then add 2, so I get 5. And if I need a sub 3, I'd need to go to 5, add 2, and get 7. Now the problem with this is, supposing I ask you, what's a sub 100? Well, to know a sub 100, you need to know a sub 99. And to know 99, you need to know 98. And to know 98, you need to know 97. So it's going to take you a long time to figure that out, which is where the explicit formula is going to be faster in that case. But writing it, this was really quick for me, right? I didn't have to calculate what term came before it. So it's kind of balanced and like where is the cutoff, right? What is the purpose in you writing it? Are you trying to write it to calculate? Because if you're trying to write it to make it easy to calculate, then the explicit formula might be better. If you're trying to make it easy just to describe it, maybe the recursive formula is better. So those are the two main formulas for arithmetic sequences. Similarly, for geometric sequences, these are like exponential functions. So like an exponential function. So for example, we could have a sequence like 2, 6, 18, and so on. Right? So here, I am multiplying by 3 every time. So this is what makes it like an exponential function. It's a common multiplier. We call this the common ratio. And again, we can label this the same way. This is a sub 1, a sub 2, a sub 3, and so on. We can write both explicit or recursive formulas for it. So for explicit, I can go to the first term. So I can say it's 2 times, so a sub n equals 2 times, well, 3 is the common ratio to the n, but I need to adjust it because I used 2, so I need to do n minus 1, just like I did with the arithmetic one. Or I could go backwards to get the 0th term, which would be 2 over 3, and then multiply 3 to the n. Either one would work. It would give me this sequence. I can also do this recursively. In this case, again, I tell you what the first term is, and I tell you to get any other term, go to the term before it and multiply it by 3. Oh, I forgot to write. So this is the general explicit arithmetic formula. For recursive, this would be the general recursive formula. So you tell me what a sub 1 is and then write what to do to get the next term. And for geometric, you can do a sub 0 times, common ratio is usually r, so r to the n, or a sub 1 times r to the n minus 1, that's the explicit. Or for recursive, you tell me what a sub 1 is, and then a n minus 1 times r. So those are the basic things for sequences that you need to know. There's some example problems here we'll go over. So this one says find the first 4 terms and then the 15th term of the recursively defined sequence. And it tells me b1 is -3. And this one says it slightly differently from how I wrote it before. This one says to get the next term, to get the k plus 1 term, use the k term and add 10 to it. It's the same idea, right? It's just telling you use a term you already have to get the next one. So the first term I know is -3. And then this tells me to get any term after that, I need to add 10 to it, right? It's telling me that the common difference is 10. So b sub 2 would be -3 plus 10, then plus 10 again, and plus 10 again. So I get the first 4 terms. That was easy to do with recursion. Now when I need the 15th term, I don't really want to go to the 5th and 6th and 7th and 8th and so on. So I'm going to write an explicit formula for this. So I know that it would be -3 plus 10 times n minus 1, or k minus 1 in this case, I guess. Right, because -3 is my first term, and then I want the 15th term. I know the common difference is 10, so I need it -1 because I started with the first term. So I plug in 15, so it would be -3 plus 140, which is 137. Next one, I have a sequence given to me 3, 6, 12, 24. So looking at this, I can see it's multiplied by 2 every time, which means it's a geometric sequence. I can write both explicit and recursive rules. So let's do the recursive rule. So for recursion, I start with my first term, which is 3. And then to get any term after that, I need to multiply it by 2. For the explicit formula, I can write it as first term times my 2 that I need to multiply every time to the n minus 1. Or I can go backwards. 3 halves would have been the 0th term times 2 to the n. Either one. So hopefully that gives you an idea of sequences. If you had any questions about it, hopefully this answered any questions you had.